implementing those, we'll
We'll have what?
at that point, if you stop screen share, then we can pin.
Oh, exciting.
Yeah.
Okay. Well, welcome to this discussion. I was confused for the longest period of time because there's 2 people in person and like, what, 7 online. So I guess as one of the students brought up, it is in fact project week or project deadline today. So maybe that's probably why. But you know, this discussion will be recorded. So if you are here and you feel like you really want to go work on the project instead, it's totally okay. But yeah, getting into, I don't know why I have a Zoom back there. That's from last semester. Getting into crypto. So I know, again, this is a Friday discussion. So we're talking about stuff that was covered last week. So from my perspective, we just started cryptography. So we get to go over cryptography again, even though we're like already halfway through crypto for lectures, but that's totally okay. The main idea behind cryptography is that we are going to define some adversary, but we're never going to make an assumption about them. And modern cryptography today is basically a bunch of reduction terms. We say that if the adversary can do this, then like they've broken this fundamental law of mathematics. So thus, you know, breaking it shouldn't be possible. And nothing in that statement has ever made an assumption about the adversary. So you get these really strong guarantees that it is literally mathematically impossible for the adversary to say, read your messages or change your messages and so on and so forth. So in cryptography, we're going to rely on this thing, or not rely, we're going to assume this principle called Kirchhoff's principle. In short, the adversary knows everything about the encryption or everything about the scheme in general, except for the secret piece of information that we call the key. If you think again, all the way back to lecture 1, this is the same thing as Shannon's maxim, but it's more specific because it's crypto and we have this hidden portion called the key. So we call it Kirchhoff's principle. We have 3 main goals that we try to achieve through this. Confidentiality says that the adversary can't learn anything about the message given the ciphertext. So if I send something to, what's your name again?
Al.
To Alan?
Al.
Al? If I send something to Al, I don't want anyone, say, I don't want Ron to read our secret communications. Sorry, Ron. We do say that Ron can learn. I don't know why we're using Ron. I'm sorry, Ron.
It's okay. I'm an eavesdropper right now.
We'll say Ron can learn how much data I'm sending because it's really hard to hide that information. We also have integrity. So if I send a message to Al, say, hey, you know, discussion is at 4 p.m. today. I think it is, yeah. Ron can't change it and say, oh, discussion is actually at 6 and like, you know, make you come to soda at that hour. And then there's authenticity. So somehow you maybe can verify that I sent the message and not someone else. And this is really closely related to integrity because, you know, if you can change a message, then it doesn't matter what the identity appears to be because then anyone could have sent that message by changing it. So they're very closely related, but they're still distinct concepts. Questions about any of that? Cool. Okay. So getting into symmetric key crypto, there are 3 main elements. The first one is keygen. Pretty simple. You just generate a key. For most symmetric encryption algorithms, it's just going to be generate a bunch of random bits, and then that will be the key. We have an encryption function, so we say encrypt the message M, and that outputs the ciphertext C. And we say there's a decryption function which takes the key and the ciphertext, and we need to decrypt that back to the plain text. Now notice that both of these functions take the key, but Mallory doesn't have the key K. Mallory can't perform either of these functions. That's why we call it a secret key. There are some properties. Correctness says that if I encrypt a message and then decrypt it, I want to get back the original message. Hopefully it's somewhat intuitive why we want that property. And for security, we have something called INCPA. And there's some algorithms on there that I think we'll get into a bit more later. So INCPA, it's this abbreviation that stands for indistinguishability under chosen plain text attack. And I'll break down what those words mean in a moment. Chosen plain text attack means that the attacker can ask for the encryption of any plain text. Now, when you first hear this, it's like, why would that be a reasonable thing for the attacker to do? And One example might be, say, the adversary has the ability to send you emails. So, my computer's hard drive is encrypted. What was your name?
Aditya.
If Aditya sends me an email, that email gets stored on my hard drive and that gets encrypted. So, I didn't have any say in it. You've just caused your email to be encrypted and stored on my computer. Maybe if you steal my laptop later, which please don't do that, then you could, maybe oh, the email's stored here and I can learn that this is the encryption of my email and thus I can break your encryption. So if you think about it a bit more, it's actually a pretty reasonable model for the attacker.
Huh.
Ghosts, I don't know. Now, how the adversary is allowed to work is we define this game that the adversary and the challenger are going to play. So at the beginning, we have this sort of before the message pair, we have this first round where the adversary is allowed to send as many messages allowed to send as many messages as the adversary wants, and then it'll get back the plain text, or the ciphertext, sorry. Eventually, the adversary has to say, okay, that's enough. I'm going to send two messages, message 0 and message 1. Now, the challenger, they're going to choose one of those messages and encrypt it and send it back. But the adversary is not going to know who it is. So the challenger chooses randomly. At the end, the adversary gets to send a couple more messages, so maybe they can use this to learn some info. And then eventually they have to guess, was message A or was message 0 encrypted, or was message B? Was message A encrypted? Wait, was message 0 encrypted, or was message 1 encrypted? Sorry, there are a lot of numbers and letters going on. And the idea here is that if the adversary can look at the ciphertext and tell, oh, this must be message 0, but not message 1, they've learned something about the message from the ciphertext. And we don't want that. We want to say that the adversary can't learn anything about the message. So if the adversary can gain any advantage in this game, then this scheme is by definition leaking information to the counter. Questions on why this is an intuitive game for leaking information or how this game works in the first place? Okay, cool. That's enough info. Hope there should be a discussion sheet slide in there. Just for flow reasons. That's enough info for us to go through the first question. So do both the sheets. So this first question is talking about in CPA in general. We're not talking about any specific scheme. So take a couple minutes to work through it. Feel free to raise your hand if you're in person, put a message in the chat if you're online, and I'll be happy to answer them. We'll probably spend, let's say, 10 minutes working on this.
Can I pin it on your Zoom?
Sure. I think you can also pin me on your Zoom.
I pinned it on mine, but I think you're the one recording.
Oh, did you do spotlight?
How do I do that?
Oh, there's like a button. Oh, spotlight for everyone.
Spotlight for everyone.
Yes. No,
Thank you.
It's basically force pinning for everyone.
That's beautiful. Thanks, Nicholas.
They usually use this like fancy handwriting for the adversary. It's like this, something like that. We'll just go with that. I just realized you're in the wrong direction. It's fine. It's fine. Imagine that. Imagine if we had a cryptographic scheme that was secure if you drew it one way but not the other.
Mhm.
Worst in the world. I'm just really bad at drawing that. Oh. Yeah. Ooh, look at that. I get a thumbs up if you're done. And a number of fingers equal to the number of minutes you think you will need if you are not.
And that includes to folks virtually, if you are not done, please let us
Yeah.
know how long you want.
All right, well, in that case, why don't we get started? Yeah, sorry, took a moment to figure out what I was trying to do. Okay, so we are defining this scheme as the encryption of M under K is just M X over K. So this is, it says it's similar to the one-time pad. This is in fact exactly equal to the one-time pad that we taught in lecture. But you'll notice that, you know, in this case, we're saying we can use it as many times as you want. So you might already remember that, hey, this scheme is not really secure. So we're gonna say we want to break this in the NCPA. So the first question is asking, we get to choose two messages, M0 equals something, M1 equals something. What do we want these messages to be? Yeah, so in NCPA, they have to be the same length because we're saying they're allowed to leak length, right? And there might not be like a single correct answer. There could be any number of answers. And let's just go with whatever someone suggests. Okay, well, let's say that in that case, I'm going to choose M0 is equal to 0. Let's just say that this is a, let's say it's like a 128 bit message. That would be the specs for that. So let's say M0 is 128 zeros. What would we want M1 to be? Or what could M1 be for us to win the NCPA game?
I felt like the actual values don't really matter because like when you send the same message, like you get the same encryption.
Right, but we're just going to like provide a full counter example. So remember, we just need to show one example to show that's insecure, right?
Oh,
So we could like say M0 equals M0, but let's try to, I think we're trying to come up with a more salient example. So if I just said M0 is going to be a bunch of zeros, what could another M1 be? Sure, why not? 1 to the 128, 128 words. Great. Now, down here, we get to ask for just more messages. So let's say now we get back MB is either 0 to the 128 or 1 to the 128. Actually, that should be the encryption. X or K, 1 to the 128, X or K. All right, that's the second text we get back. It's either this one or this one. Now, what's another message that we might want to send in order to distinguish which message was encrypted? Sure. So let's send equals, why don't we do the first one? 0 to the 128, which is also equal to 0. We'll get back C equals 0 to the 128. X or K. All right, so we received this. Let's say this is our CB. What would be the final touch to our algorithm? I think we went a little bit out of order here, but okay. What would be the final touch to our algorithm? So we have this info is either this one or this one. And we have this info of the encryption of 0 to the 128 is 0 to the 128 X or K. Yeah, so we're saying if, and we can literally write it out as like pseudocode here, which I'm just going to write as Python because I don't know the pseudocode. If, what do you think? C is equal to CB, then yeah, so we're returning, in this case, 0, because we're trying to guess B here. Else, return 1. Okay, I literally don't know how to write English. 1. And how often will this guess the message correctly? Yeah, in this case, in with probability 1, and that's greater than 0.5. Thus, the scheme is insecure. So this is kind of like a full proof that you might walk through to show, hey, one-time pad, not NCK secure. You should not do that. Well, does this make sense? Any questions?
What is CB?
So CB is going to be either the encryption of M0 or M1. And in CPA, we send 2 messages. We get back one of them, the encryption of one of them. And if we can tell like, oh, this must be M0, not M1, that means by definition, we've learned something. So we don't want to learn anything. In this case, we can learn something. So yeah. All right, so that's the first 4 parts, I think. Yeah, and 1.4, I guess we can just go over it really quickly. This works for any deterministic algorithm. So we notice if it's deterministic, we can always check, is the message that I just asked for equal to the challenge message, then return 0, else return 1. So any deterministic scheme, by definition, cannot be in CPA secure. We've just kind of proven that all deterministic schemes are insecure. All right, so in the next instance, we have can I erase this by the way? Sorry. In the next instance, we have, oh no, it's not erase that. Some adversary that can win the, interesting, there's a typo on the sheet, it's okay. There's an adversary that can win the game, not like with probability 1 that we just did, but with probability 0.6. Is this secure? No, right. The idea here is that even if the adversary can't guess correctly like 100% of the time, if they can still guess correctly with, better than random luck, then they've still learned something. Maybe they haven't learned, the entire message, but they've learned like something that could give them a better than random chance. And this is, information theoretically leaking information. What if it wasn't 0.6? What if there was an adversary that could win with probability 0.4? So let's say like A wins with probability 0.4. Is this, if there exists an adversary that can win like this, is this the secure scheme?
No.
Why? And how?
If you just reverse or guess every time, it's 0.6 something.
Sure, okay, so let's say we have an adversary A prime, and that basically what they do is, what did you say?
Just whatever the algorithm is, just like reverse the guess.
Sure, so if A outputs 1, then just return 0. 0 else, return 1. So I guess what this shows is not only does the probability have to be no more than 0.5, it has to be no less than 0.5. So in fact, it has to be equal to 0.5 within a margin of error, which is very, very small. All right. Final question. Let's say that there's an adversary that, they choose an algorithm and they only win with probability 0.5. Is this an NCP secure scheme? We got one nod. Any other? Okay. So this question is a little bit finicky. What we've said is that I'm going to use CS70 syntax here, but it's okay if you don't know it. What we're saying is there exists some adversary such that the adversary wins with probability 0.5. I don't feel like reading the rest of that enough. But in order to prove security, do we just have to show that, some adversary only wins with probability 0.5? Or do we have to show something a little bit more robust?
We want to show the probability A winning is equal to the probability guessing with.
Right, but if the adversary has, so we're saying there exists one adversary such that the probability of winning is 0.5. Is that sufficient to show security? Ron, by proxy?
On in this case, we want to show it for all adversaries.
Yes, exactly. So it's not there exists an adversary that wins with probability 0.5. In fact, we want to say for all adversaries, the probability B prime equals B, which is actually what I was supposed to write over here, is equal to 0.5. And that's why it's sufficient to say that we only need to show one adversary can win with probability greater than 0.5, because that's the counterpositive of the statement. Because that shows that it's not for all adversaries, because there's at least one that does not satisfy this. So I know the wording of the question was a bit tricky, but it's sort of trying to get you to think about, how do we actually show security? Yes.
So just by these tests, you can't prove that something is, NDVA.
Yeah, it's not like we can just write like 500 adversaries, and none of these could possibly, and none of these were able to gain an advantage. That's not sufficient because of the infinitely many adversaries that could be. We need to show that for all of them, they cannot get an advantage, and that's really what's so neat about cryptography. All right, so block ciphers and modes of operation. That was sort of a theoretical high-level overview of block ciphers. We're going to get a bit into how we actually construct some of these. What? Oh, yes, that's because I jumped forward a bit. Never mind, discussion's over. All right, block ciphers and modes of operation. So block ciphers are this construction that takes in a k-bit key and some block M and outputs a ciphertext block C. And it's not like an encryption algorithm because this has to be a fixed length. So we define, let's say, AES. M has to be exactly 128 bits, and C has to be exactly 128 bits. The key doesn't have that restriction. You can actually have any size of key that you want. Or it's defined by the block cipher. But the idea is this length has to equal this length. And we'll get into some of the other mathematical properties that block ciphers will have. So one is it has to be deterministic. You'll notice that there's only a message and a key. So there's no actual like randomness going on here. It has to be bijective. So this is a fancy CS70 term that you may or may not remember from that class. But the idea is if we like write out all of the possible inputs and all of the possible outputs, this has to be a one-to-one mapping. So let's say maybe that encrypts to that, that encrypts to that, that encrypts to that, and that encrypts to that. You can't have something that does, say, this. This simply wouldn't work, because if I try to decrypt this, like, what was the original message? Was it 0, 1? Was it 1, 1? I don't know. So it has to be, the fancy term is a bijective function. So for something like AES, the block size is 128. And if we want to be able to encrypt arbitrary length of messages, you know, remember I don't always want to send 128 bits, then we need something called modes of operation on top of this. So this is like a primitive that we'll use and we'll build on top of this to have more robust encryption schemes. So the first one that we talked about was something called ECB. This one is fairly similar or fairly simple. If we just have a bunch of messages, we encrypt all of them with the same thing, same key, and we just say, you know what, good enough. If I have 128 times 3, 384-bit message, then we'll just break it up into 3 blocks and encrypt them all individually. We saw very quickly why this is super insecure, and that's because, like, if say this block and this block are the same, then these 2 blocks are either the same, and that's enough for the adversary to be able to distinguish or to win the NCPA game. So very insecure. I know it's like really intuitive, but don't do this. CBC mode of operation. This one's a little bit more fancy. We're saying, okay, well, we know when this is encrypted with the key, this looks kind of random. So why don't we, if this is unpredictable, we'll just take this, bring it up here, and XOR it. And now, you know, this looks random, so this input is unpredictable, so this output must be unpredictable. Why don't we take this? Oh, not that. Why don't we take this, bring it up here again, and XOR it with the next one, and so on and so forth. And this is a little clunky, but it actually works. And that's kind of the intuition that I was saying, because this is unpredictable, this input's unpredictable, so this output's unpredictable, so this one, and so on and so forth. We already showed the decryption scheme in lecture, so I won't go into it too much, but this is an NCPA secure scheme. Final one's a little bit more fancy. So when I first learned about this scheme, I felt like betrayed because we have this block cipher, but we never like passed the message through it. We only passed like this fixed to data. So the way it works, we have our thing, we have an IV, and we're going to concatenate it with 0, and we're just going to encrypt that. So the message never goes through this block cipher. We just get some output, and we XOR it with the message. And we get our ciphertext. Keep it in there. And then we're going to do the same thing, take the IV, concatenate it with 1, pass that to the block cipher. We get out C1, C2, 1, 2, 1, and so on and so forth. So again, I felt betrayed because it was like, we have this fancy like block cipher scheme, but we're never actually encrypting the message with it. But it turns out it's still secure. Part of that because of XOR, and I'll get into that in a moment. The idea here is that the adversary knows what's going into this block cipher, but because they don't have the key, this output is still completely unpredictable to them, and there's no way they can arrive at this output themselves. So when you take this and you XOR it with a message, then this, because of the way XOR works, this output is also random and unpredictable. So even though we're never passing the message through the block cipher, it's still a secure scheme. It's still NCPA secure. And you'll notice the nice thing here is that, you know, I can draw a line straight through here. All of these are basically individual operations. So if I had, say, 3 CPUs, let's say 4 CPUs, that's a very different number. Then I could have this CPU encrypting this one, this CPU encrypting this one, and this CPU encrypting this one, and it'll all be done in parallel. So you can get really good parallelism with something like counter. So those are the main schemes that we taught in lecture. What the second question is we're going to give you a new scheme that you haven't seen in lecture before, unless you reviewed, say, last semester's lecture. We're going to ask you to draw the encryption diagram to get you a feel for how that works, write out the decryption formula, and analyze a couple of the properties of it. So we'll spend, let's say 7 minutes working on this, and then another 7 minutes going over the answers. And as always, feel free to ask any questions if you have any in the meantime. Yeah.
Enable transcription.
Oh, yes. I wish there was a way to do that by default. I keep forgetting.
I think there is a way. I just sent a request.
Yep.
Thanks.
Yeah. I feel like Zoom should just do that by default.
I know, right? I don't understand why they wouldn't.
Yeah. I mean, it's not great. Not gonna lie, but it's better than nothing.
So, for E sub k, what does that mean?
E sub k.
That's just some sort of function.
Yeah. So that's the individual block cipher. This block here, we're calling it E sub k.
Okay.
And it's different from enc that takes in k, because we're trying to write it out more like a mathematical function because it's a one-to-one function. It's just to distinguish it from a real encryption scheme.
Got a question.
Go for it.
Go back to like this slide.
Yeah.
Like, third, like, the question I have is, why do you need IV?
Why do we need IV? Yes, very good question. So remember in the first question, we said that deterministic schemes cannot be secure. Right. So if I encrypt the same thing twice, I need to somehow have some randomness that says that the first time I encrypt it is different from the second time I encrypt it. So this is that source of randomness. It's deterministic relative to the message and the key and the IV. So if all three are the same, I'll get the same text out. But we're saying this one will change every time. It's completely random. We used to do a question. I just realized we used to do a question I really liked, and it's not with us anymore. It was about, can you have a IV that is predictable but unique? Ooh, damn it, what that question again? Sorry, I'm gonna send a message.
That's a
inside.
good one,
I really like that question.
Every couple hours, someone's like, the queue's on fire.
Yeah, it's today's last day.
Yeah. What you looking at?
Speaking of the screen, I'll stop sharing it.
Nonsense here, nonsense idea is
Kind of.
Kind
Kind of. We can go to the into that distinction at the very end.
I'm curious.
It has to do with that like predictable but unique thing.
Um,
Spoilers, the requirement for a nonce encounter mode and an IV and CBC mode, they're not the same requirement. They're ever so slightly different. Well, I don't need the projector anymore. Anyway. Whew. You do the same thing. Just thumbs up if you're ready.
Sorry.
Oh, thumbs up if you're done with the question. 2 out of 3. I can wait a bit longer. 2 out of 3 plus however many on Zoom.
Why don't we keep the three field names? You know,
Project 1 is due today.
all there out.
Yes, and given that the office hours queue is currently flooded, that is probably the reason. Yeah.
This project team much harder than project two.
Project one is a kind of puzzle solving. So if you like, as it like, you know, having been through the project many times, I could do it in like 10 minutes because I know what to do. But for most, like, so the bulk of the time is spent like, how do I actually do this and not know how to do it.
Yeah.
Project 2 is like design. If you took 61B and had the GitLab project, it's similar in spirit to that. Yeah, you can kind of think of it like a 61B project, but a lot.
One of them is like a long project, one of those like project.
Yeah, so 1 and 3 are like puzzle solving. So it could take 10 seconds, it could take many days. Project 2, it just takes many days. Project 2 is also the heaviest project. I would put it in the middle because I know every other class puts their heavy project at the end. Yeah. All right, in the interest of time, why don't we get started? So we have, quickly, we have our mode called CFB mode. It goes, how's it go? Yeah. CI equals C0. Wait, what? Ah, sorry, I'm used to writing it differently. C0 is just equal to the IV. CI is equal to the encryption of the previous ciphertext block XOR with PI. All right. Who wants to draw an encryption diagram? Sure. I'll draw your boxes out for you. All right. Give a thumbs up if you agree with this. No one agrees with this?
We got a middle one.
We got a middle thumb? All right. Well, I think one thumbs up we can have. Yes, that is exactly correct. Technically, you would have to say like this is encryption. Because some schemes might use decryption for something. Or it's more important for the decryption diagrams, but yes, this is all block cipher encryption. All right, what would the decryption formula be? So how do I, given CI, how could I find PI?
So you decrypt the last CI.
Come in?
You don't decrypt the last CI.
Okay, so E I minus 1.
It's over CI.
Yeah, XOR with CI. So if you ever, so one way you could do it is look at this and then just think about it for a bit. The easier way would be to use algebra. So if you think back to a long time ago, if you do the same thing to both sides, you'll end up with something that's still an equation. So we see we have this like well, this blob here XOR with something. Remember that XOR cancels itself out. So if we XOR this side with E, K, that's too long. And we XOR this side with the same E sub K of CI minus 1, then this encryption and this encryption cancel each other out, and then we're just left with this on this side. So you can literally use algebra to solve this. If you ever needed to cancel out an EK, you could of course use DK, because DK, and M equals M. Hopefully it equals M, otherwise you don't have a valid block cipher. All right. Now, what is true about CFD mode? Thumbs up if you think that we can parallelize encryption. I'll have a thumbs down if you don't, and thumbs up if you do. All right, not all thumbs down. What's your intuition? Anyone? Really violent. What's your intuition? Why don't you think this can be parallelized?
CI minus 1 to decrypt like C.
Yeah, exactly. So the way I would look at it here is, okay, I want to find this. And what I need to calculate this, is actually the previous one. So I can't do it, I have to do it sequentially. What about decryption? Thumbs up for yes, thumbs down for no. All right, we got yes. So if you drew it out, it would be pretty apparent. But I guess what we want to see here is the plaintext. You don't need any other plaintext blocks in order to solve for this. There are some modes that you actually XOR with the previous plaintext block. But this one you don't, so we can parallelize. Now, this one's a little bit tricky, but do you think this is in CPA secure? And you don't need a proof, obviously, but thumbs up for yes, thumbs down for no. Thumbs sideways for I don't know. All right, we got kind of the yeses. I'll help you out with this one. So it's the same sort of intuition as CBC mode. And we have the IV, which is unpredictable. That gets encrypted, so whatever's output here is unpredictable. We XOR with something, but remember XOR is sort of special in that it doesn't, make it any less random. So this is still unpredictable, so that's unpredictable, so this is unpredictable, and so on and so forth. Again, very intuitive, very like hand wavy explanation. There's a formal mathematical proof for this, but that's sort of the high level overview. And we'll never ask you to write like a proof for on an exam. What happens if, I guess we're saying nonce here, but what happens if we encrypt, so we have the same nonce, which is the ID, and we have the same message, what's going to happen to the ciphertext? Or I guess what's going to happen to the scheme?
So if the first couple of blocks of the plain text is the same, then the first that many blocks of the C would be the same thing.
Exactly, yeah, it's very similar to CPC mode. If this input is the same, and this input is the same, and this output is going to be the same. And if this input as in the plain text is also the same, then the first ciphertext block is going to be the same. And we can already see that that's not going to be in secure anymore. But if this input is the same for both, sort of by the same logic, the second one is going to be the same if the plain text blocks are the same. So until they differ in one plain text block, the adversary is going to be able to distinguish are the blocks the same or not. After that, you sort of get the same security guarantee for the block. Right. What happens if they use the same IV but not the key? Or sorry, that's not what the question says. If they learn the IV but not the key, what's going to happen? Is the scheme still secure? I got a nod. Why are you nodding?
Is not like when you use this like ID, then become random. You don't know anything about. You don't know anything.
Okay, but we're saying, okay, so we don't learn anything about the IV from here. But we're saying, let's say somehow the adversary manages to learn this IV anyway. Does this scheme still remain secure?
I think it's just for a given encryption, like one given encryption, as the question says, like, yeah, it's still secure because you can't, because the only thing you can say if there's multiple would be like if they're the same, like the messages are the same.
I think. So you're saying like if it's just one message, then what?
Then it's like perfectly fine, and you won't know anything about that.
Well, so we're saying like, can they decrypt the message if they have the IV basically?
Yeah, no, they can't.
They can't, right? Because they're missing this key. And sort of the other thing to notice here is that the adversary, in fact, does learn the IV. I really like this arrow because most people don't draw it. I actually usually don't draw it. But the adversary learns what the C0 is, and this C0 is just the IP. So it's the same as CBC mode, it's the same as counter mode. The adversary can, in fact, learn the IV, and that's fine. The IV is just there to introduce randomness. It's not there to be secret. All right, that is the end of the discussion sheet. I did have a feedback link, but unfortunately the screen is not working. So if you want to send me feedback, feel free to like, I don't know, encrypt the message and leave it somewhere, and I'll decrypt it with a secret key or something. I don't know. Any final questions on anything? On Zoom or in person?
Feel free to unmute and chat if you want to. Nah, folks are just leaving.
All right, see you everyone. It's okay. Oh, great, we're gonna end the recording with that. I'm so excited.
Thank you.